All right, so today's lecture is on induced electromotive force and the electric field. So we're going to start with a loop. Okay, and we're going to make it as circular as possible. Okay, in fact, we want it circular so it has this radius r. Okay, and it is in a magnetic field. Okay, but this magnetic field now, okay, is not just a magnetic field, but it varies. It is a variable electric field. It varies, and we're going to give it a function of 2 Teslas per second t. Sorry, I shouldn't have put that there. Okay, that the magnetic field is now a function of time. And it is changing by 2 Teslas per second. All right? Now, if that's the case, then now also, if it's changing per 2 Teslas per second, that means it's changing in which direction? Okay, well, if our x's are into the page, then it's changing into the page, right? Okay, so that's going to make our current go in which direction? So our fingers, remember, we want our fingers to be inside the loop, right?
Clockwise. Clockwise. Counterclockwise. Clockwise. It's clockwise. Inside. Boom.
Wait.
It's clockwise.
It's
clockwise. It's clockwise. It's clockwise. I bet too.
$5. I'm not making money on this. I'll be sorry.
If we remember from Lenz's law that the induced current comes in to counteract the change of the magnetic field. Our magnetic field is pointing up. And so, if we have a particle at this point, the force that is going to exist on this particle is going to point in that direction. And then if it's here, it's going to move that way, right? Okay, this would be counterclockwise. Okay, so I'll take my farm now, thank you. For those of you that bet the farm on you. Okay. So the change is going to be up out of the page, because if we're increasing this way, if we're increasing that way, then the induced current is going to counteract the change, which will be in this direction. And for it to go in that direction, it has to go fingers up, curls around, grab the wire. Okay, the current goes in that goes in the counterclockwise direction. So all of these experience a force in that direction. Okay, now if they are moving in this direction, so remember that our EMF then is equals negative d phi dt. Okay. But what is phi based on? Okay, phi. Okay, is B dot A, which is our area, right? So in this particular case, our phi is going to equal Okay, and I'm going to drop the units for right now just for just for some simplicity's sake. I'm going to drop these units. Don't do this. Never drop the units on your test. I'm at the point where we've done all these lectures. I'm finally going to drop the units. Okay, our field is 2t, right? 2t. Okay, times the area, but what's the area of this loop?
Pi r squared.
Is pi r squared. Okay, so our phi is equal to 2 pi r squared times time. Yeah? It's times time. All right. Well, if this is what our phi is, and our EMF is negative d phi dt, okay, then this is negative d dt of 2 pi r squared times time. Yeah? Okay, well, what's that going to be? Our EMF equals negative 2 pi r squared. Okay. Now, that means that our delta V, okay, or we've learned earlier that our delta V is also equal to, gosh darn it, delta V is equal to our field times our ds, right? Remember this one? Yeah, for it's we're setting the Wayback Machine here. I get that. Okay, or actually we're setting it to yesterday. Didn't we have this yesterday? Let me check my notes here. No, not quite. No, we didn't do that one yesterday, but it's there. Yeah. But if we go all the way around this loop, doesn't this become a line integral? Okay, where this would become our EMF and our E is equal to and this is an exceedingly profound statement. This is the actual complete Faraday's law. Okay, yes?
Why did you need a formula for E if you didn't use it?
Sorry?
Why does the EMF have to be negative 2 pi r squared if it's not in that law?
Just for fun.
Well, sorry. Let's try, I didn't work it out. What is the ds going to be right here? Okay, so, right. Right, circumference, which would be how much? 2 pi r. Okay, and so our charge, okay, so if our field, okay, is going to be based on our field is going to be based on the distance from the charge, right? Which would be the other r. Yeah?
Yeah.
Okay, so that's where this is coming in. It's to show the relationship of the 2 pi r and show that that's the ds. Okay. If you integrate 2 pi r, you get pi r squared, which is the area. Yeah. Okay. Which is the other way of thinking about it conceptually? Is that if we're integrating this, we get 2 pi r, right? But if we're taking the derivative of this, that's related to the area, right? Okay, well, the time kind of, but Okay, but that's how they're getting these related. Faraday did the hard work. Okay,
Does S and T cancel out on top?
S and T.
The very top.
Yes.
So S stands for second.
Yeah, Teslas per second. Yeah. Okay, this is the complete Faraday's law. Okay. Why am I having a hard time explaining this right now?